PHY-105 in the beginning of the year, I think in March something. And then after about 6 months, he had another thought that that theory has another consequence, very profound one regarding energy and momentum. And of course mass as well. Energy, momentum, mass. So this is what is going to be our topic today, and we'll see how we can say and what does it mean to say mass and energy are equivalent concepts and they are together conserved. Not that energy is conserved separately and mass is conserved separately as we used to think in the classical relativity. But before I go there, I actually want to say a few words about what we are not studying in this course and which is very important and you might study in some higher course. So what we are not studying or what we are leaving out are many simple things as well, simply because we don't have time. We want to concentrate on quantum physics, which is still about a week and a half away. So let me tell you what we are skipping out. So we have seen that if we have a frame which is moving with speed v with respect to another frame, and we know that if two events happen at the same position again and again, we know how to translate the proper time into the other frame, or we can translate the proper length to another frame. But what if one event happens here and another event happens here little bit later than this? How do we transform this time difference to this frame, or how do we transform this length difference to this frame? So for this, actually there is a general mechanism which is available, which we are not actually going to do in this course. It's called Lorentz transformations. So they actually relate one point with coordinate to another point in this frame with these coordinates, and there is a set of equations. So we are not going to do that, which transforms the general pairs to here to there. And also, what if something is moving with some velocity u here? What's its velocity here? Or what's the law of velocity transformation corresponding to the Galilean addition of velocity law? So there's a slightly complicated velocity transformation law to transform velocities from one frame to another frame. And we are also leaving out that, and a lot of physics that is connected with Lorentz transformation and these things. The idea in this course is to give you a survey of the laws of modern physics. And what we have covered in time dilation, length contraction, that pretty much sums up what we get from this, and that is still the basics of what is here. So I'm saying it because in your book, when you see chapter 1 or 2 of the main textbook, there's a lot of stuff that and problems that require this thing. You don't have to do that. Or is it a velocity transformation or is that चीजें हैं? So we are not going to do that. हम दो special cases ले रहे हैं. One is the rest length, contracting in another frame, and the other is proper time interval, dilating in another frame. और फिर हमने उसकी consequences जैसे देखी हैं Doppler effect में. अब Doppler के बारे में आप में से काफी लोगों के सवाल हैं, especially that why we take one proper and not the other. So the reason is this. For example, if this is the observer and this is the source, since light is being emitted by the source at one point, while source and observer are in relative motion, so it doesn't make sense to say that this is stationary and this is not. All we can say is that there is a relative motion between the two and there is a relative speed. But the time for this source is proper because you see what source is doing. Let's say source has a clock on it and it's moving with respect to us. it's moving or not doesn't matter. And it's say let's start counting now, and it's sending pulses, sending crests of the light. It's going like this. Maybe it sends 1 million periods in, let's say, 2 minutes. In 2 minutes, it's gone from here to here. So for this is a proper, these are proper events, because the light is being emitted from the same point, while it's here or here or here. So that's why the time interval for this is proper, and the time interval for observer is not proper, because the light started coming out here, and it's now coming out from here, it's coming out from here, and we are trying to measure the wavelength or distance between these two intervals, or if we call frequency, the time interval between two events that have happened here. So that's why we said that the time here is proper, and here it is dilated, and we use T prom is equal to gamma T naught. So that's the reason, because the source is emitting and it's moving with respect to the observer. So its time is proper for the source and not for the observer. Okay, so let me get back here to our main topic here. I'll actually upload another chapter of a book which has only the basic stuff that we are talking about in this course. It's still another book, very easily written, so I think that would be more appropriate than the main textbook, which has 2 chapters on relativity. लेकिन सिर्फ एक टॉपिक है जो हम next class में करेंगे, which is on general relativity. That would be from the main textbook. तो मैं एक ही जो है वो bundle PDF बना के upload करूँगा for relativity, जिसके अंदर जितना भी हम इस कोर्स में कर रहे हैं, that is included all. So for relativity, you only have to see that and not the survey textbook or the Randy Harris textbook. Okay, so let me get back here. When we use the Lorentz transformations, which are here, which actually come out like this. That it transforms like this. So this is how the time and space transform into time and space in this frame. So when we use, these are the Lorentz transformation which connects the coordinates in one frame to another frame. We are not going to be bothering about this. Based on this, we can find the velocity transformations, which are something like these. Let's say this particle has an x component and a y component and a z component of velocity. So the x component would transform something like this, and y component would transform something like this, and z component would transform similarly. So these are velocity transformation laws which replace the Galilean transformation law. For example, when v is very small, you can ignore this, so you get the Galilean transformation of velocity addition. But since generally it's not small, you have to keep this part if it's relativistic. So anyway, if we use these velocity laws and we try to see the conservation of momentum. Let's say you have a billiard ball of mass m1 striking another billiard ball. So after collision, so this is the initial part, so this one will go here, this one will probably go here. So if you write the momentum like this, mass time velocity, in one frame, the momentum might be conserved in one frame but may not be conserved in another frame. So let's say in x, y, z is conserved, but when you go to another frame which is moving with speed v with respect to that frame, the momentum is not going to be conserved. Which means that this is not a proper definition of momentum, which is valid for all speeds and for all observers. So this motivated people to define momentum like this. Simply gamma mu, and if you define momentum like this, momentum is conserved in all frames. And unfortunately, I'm not going to prove it because I don't want to go into the details of these Lorentz transformations and velocity transformations. I'm trying to motivate you that why this has been defined to be like this. The reason is this: if we define momentum like this, then momentum in any collision or any interaction between masses is conserved for all observers. And since we know relativity, either Galilean or Einstein relativity, it requires one very important thing, that laws of physics should have the same form in all frames. So if the momentum is conserved in one frame, it should be conserved in another frame. If you define momentum in such a way, then it is conserved everywhere. So with this definition, momentum is conserved. So this definition was proposed by Einstein, that we should define momentum like this so that it's conserved in all frames. And unfortunately, we are not going to be able to prove it because of we are leaving out this detailed part. But this definition has a lot of implications for us now, which was realized by Einstein after 6 months after his theory, because we know that Newton's second law is this. Did you?
What is taking mass?
Mass is mass. So this u is speed. Nothing is changing. If you have gamma is 1 over 1 minus u square over c square. If velocity change, then of course gamma and u, they both change. Gamma is changing momentum. Yes. Okay, so I think you are referring to another point. In older books on relativity, what people would say, okay, let me keep the definition of momentum like this, but let me define the mass as rest mass over this factor 1 minus u square over c square, and I will say that when things move, their mass change. But people have discarded this thing because that's not really needed. So whenever I say mass, that means the rest mass. I won't say rest mass because I'm not differentiating the two masses. So when u changes, I would say momentum change. The mass is mass for all observers. Okay? Okay, so this is the definition of Newton's second law. Yes, please. So this is an older point of view. That's what I was referring to him, that people initially were happier with this thought that, let's say, we call this m naught, and we call this thing as mu, where m is this. So we interpret the relativistic momentum as mass time velocity, but mass is now dependent on velocity, so mass changes as velocity changes, but this is not needed. Why we have to say this? We can simply work with only one mass instead of working with two masses. So I'll come to your question again. So we are not going to be differentiating between rest mass and other mass. We have only one mass, and that is the rest mass. Okay, so this is the definition of Newton's second law, and let's see what is the energy of something. Let's say in my frame, this remote is at rest, and with some force, I'm moving it, and I'm only going to take one axis that is moving along x-axis. Maybe it's changing its speed. So it started from 0, it changed its speed, and then it moved with constant speed. So I'm taking a situation like this where we have, let's say, time, speed, something is starting from rest, it's changing its speed, and then it's going with speed u. So here it has certain kinetic energy k. So with this new definition of momentum, I'm going to find the value of the kinetic energy k for a particle which goes from 0 to a velocity u. And we know we can find kinetic energy by finding the work done on this particle, because total work done on this particle is stored as a kinetic energy of this particle. Everybody is comfortable with this thing? Yes, please. Yes, I am in a frame of reference where I started such that the particle started from 0. Okay? So the kinetic energy is, I'm starting from 0 velocity and going to velocity u, and I am finding the total work done on the particle in taking it from 0 to u. Is there any one of you who is not comfortable with this equation? That this is how, okay. So this f dx is the amount of work done. Let's say if I take the physical solution, this is the mass. So this is the x-axis. It's moving when it comes from here to here. In this small distance delta x, let's say I applied F force, F delta x is the work. Now when it goes from here to here, I applied another force, so I add all the work done, and adding is by integral in general. So this actually sums up all the work done. So this is what is going to be stored as the kinetic energy in the particle when the particle is moving. So now I'm going to actually evaluate this integral using this definition of force, which is the rate of change of momentum. So, and to do that, I have to compute this dp by dt. Yes? So, okay, so there should have been some underlying distance, but I want to work in terms of u. So maybe आप इसको आप इस तरह से interpret कर लें 0 to x or something. तो उतनी देर में velocity went from 0 to u. It's the same thing. That I'm adding all the work done when I started from 0 and went to a velocity u. Equivalently, this means that I'm starting at x is equal to 0 and going to some x is equal to something. So to evaluate this, let me first find f, and f is dp by dt, and now this is easier, but remember I'm not using a 0, but this is rest mass always. So this is the derivative that we have to evaluate. I'm going to do it quickly. So m is constant, it gets out. So we have d by dt of u, and this factor separate plus m, and then u, and then using the chain rule, okay? M is the rest mass. We are not using any other mass. We are using only one mass, which is the rest mass. So the rest mass is same for all observers, because this is a mass found at rest. So this is nothing, this is okay, du by dt, and this is 1 over 1 minus, let me just write it as half mu. इसका जो डेरिवेटिव है वो क्या होगा, इसको आप लिख सकते हैं उसी तरह से माइनस हाफ. So minus half comes here. So this is minus half minus 1. Then the derivative of this part, इसका डेरिवेटिव होगा 1 का 0, इसका होगा minus 1 over c square, और 2u का आ जाएगा 2u du by dt. So m and du by dt is common. Half. Now we are left with this u into u square, minus into minus plus. This is c square, and this is 1 minus u square c square, and this is 3 by 2 er. So you can take its LCM. The LCM is 1 minus u square c square 3 by 2. So इसको इससे डिवाइड करें तो सिर्फ ये बचेगा 1 minus u square c square, और ये 1 आ गया तो ये आ गया plus u square c square. So this goes with this. So we have m du by dt 1 over 1 minus u square c square 3 by 2. It might be a little bit boring, लेकिन मैं ये जानबूझ के इसलिए करना चाह रहा हूँ. I don't want to leave it to some homework because we want to see that by this simple thing, very interesting relation comes out that had profound implications for a lot of things, which we are going to discuss. So let me put this f in the expression for k. So now k is 0 to u, and we have m gets out. We have du by dt, 1 minus u square c square 3 by t, 2, and then there is this dx. तो ये देखिए ये है du by dt. तो ये जो by dt है ना, इसको इधर से उठा के तो इसके नीचे लगा दें. So this is nothing but u. Okay, I have made one very bad choice of variable. Okay, so I have kept the final velocity as u, 0 to u, but I'm also using the same symbol u for all the things. So let me take the top limit to be v, just to differentiate it from u. So here it is 0 to v. Okay. So this is nothing but u. So this is u, du, this thing. You saw the trick? By dt goes under it. This is nothing but velocity, dx by dt. So I get this u. अब अगर इसको आप देखें तो this is a very simple integral जिसकी कि ये फॉर्म है, आराम से बनाई जा सकती है. अगर मैं इधर c स्क्वायर से माइनस c स्क्वायर m लगा दूं और यहाँ पे कर दूं u ओवर माइनस c स्क्वायर, मैंने खुद से लगा दिया. हाँ, but to balance it, I have put a minus c square here as well. I just multiplied and divided, so I can do that, right? Because when I see this thing, I can easily see कि इसका डेरिवेटिव क्या हो, बल्कि इधर मैं 2 भी लगा देता हूँ, 2 इधर भी लगा देता हूँ. अब देखिए इसका डेरिवेटिव ये नहीं है, यही होगा ना. 1 का 0 होता है, ये माइनस 2u ओवर सी स्क्वायर आता है, तो बल्कि ये माइनस जो है ना इसको थोड़ा यूं कर सकते हैं, माइनस 2u सी स्क्वायर. तो ये u है, इसके नीचे मैंने सी स्क्वायर लिख दिया, माइनस 2 लिख दिया, बाहर भी माइनस 2 नीचे लिख दिया, सी स्क्वायर ऊपर लिख दिया. So I can multiply and divide with the same constant number. अब इसका फायदा ये है कि चूंकि इसका डेरिवेटिव है हमारे पास ऊपर, we can write its integral directly as ये वाला, ये इसमें ये by dt था ना, ये du by dt, तो जो by dt है वो इसके नीचे रख दिया du. ये I'm just trying to evaluate the integral. इसलिए कि जो इंटेग्रल है ना, अगर फर्स्ट पे आपके पास यूं हो तो दिस इज, हाँ जी मैं एक मिनट आता हूँ. सो दिस इज माइनस ए प्लस 1 ओवर माइनस ए प्लस 1. तो वो फॉर्म बनाने के लिए ये देखिए, दिस इज सम x, तो इसका ये डेरिवेटिव है. तो आई कैन राइट दिस इंटेग्रल which is minus half mc square 1 minus u square minus 3 by 2 plus 1 minus 3 by 2 plus 1 limits 0 to v. हाँ जी, ये बन जाएगा माइनस हाफ, तो ये माइनस हाफ इस माइनस हाफ से कैंसिल हो गया. सो वी हैव mc स्क्वायर, ये माइनस हाफ इसको मैंने नीचे लिख दिया 0 to v mc स्क्वायर, पहले v पुट करेंगे फिर 0 पुट करेंगे तो 1 आ गया. सो दिस इज द काइनेटिक एनर्जी. Why clapping? Because this is simple stuff. तो मुश्किल काम करे तो उसको दाव तो नहीं चाहिए, आसान पे तो नहीं. सो मैं दोबारा से आपको स्टेप्स वॉक थ्रू कर देता हूँ. सो वी हैव अ पार्टिकल which goes from 0 to a certain velocity. मैं शुरू में उसको u कह रहा था, but later I switched to v. It goes from 0 to v. उसकी हम काइनेटिक एनर्जी फाइंड कर रहे हैं. We have F is equal to d by dp by dt. उसको हमने f dx जो वर्क का फार्मूला है उसमें पुट किया and just integrated and computed all the work done. For that f के लिए आपको dp by dt चाहिए. So this is dp by dt. Just derivative लिए ये आ गया. And then I put this in the integral. तो ये जो du by dt है, dt इधर लिख दिया, this becomes u. So this is u du. अब इंटीग्रल को देख के पता चल रहा है कि इसका डेरिवेटिव हम ऊपर आराम से बना सकते हैं. अगर मैं ये माइनस सी स्क्वायर और 2 लगा दूं और कंपनसेट करने के लिए बाहर भी लगा दूं. अब देखें इस फंक्शन का डेरिवेटिव ऊपर है तो आई कैन राइट इट्स इंटीग्रल इजीली के फंक्शन में एक ऐड किया और इसी नंबर से ये डिवाइड कर दिया. So the limit is 0 to v. So this is minus half. So this minus half cancel with minus half mc square. ये भी minus half है तो इसको मैंने 1 over कर दिया. अब पहले लिमिट v पुट की फिर लिमिट 0 पुट की. अब इसको थोड़ा सा यूं करके लिखते हैं. So the kinetic energy is gamma mc square minus mc square. So when Einstein reached to this equation, he and subsequently other people also reasoned that there is this term which is velocity dependent and there is this term which is velocity independent, and both have dimensions of energy. So and the kinetic energy is nothing but a difference between this velocity independent and velocity dependent term. So this term he referred to as the internal energy or the total energy or the rest energy. So there are several names of the particle. So this is what we call E is equal to mc square. So this is the rest energy, that even when the particle is at rest, it has some internal energy. We'll discuss more about it, what does it really mean and where this energy comes from. But if I put this E here, and I can now also see that the total energy, अब देखें अगर आप रेस्ट एनर्जी इसकी डिफाइन कर लें mc स्क्वायर, तो जब ये पार्टिकल मूव कर रहा है तो इसकी टोटल एनर्जी क्या होगी? इसकी काइनेटिक एनर्जी प्लस इसकी रेस्ट एनर्जी. सो द टोटल एनर्जी, and I'm going to use the same symbol E, is kinetic plus mc square. और अगर ये काइनेटिक का फार्मूला यहाँ पे पुट करें तो व्हाट इज E? E is ये माइनस mc स्क्वायर से कैंसिल हो जाएगा, इट्स गामा mc square. So when a particle is in motion, its total energy is gamma mc square. और अगर फर्ज करें वो मोशन नहीं है, जीरो है, वेलोसिटी जीरो है, तो जीरो वेलोसिटी पे गामा क्या होता है? 1. Right? When gamma is 1 over 1 minus v square c square, तो v0 तो this is 1. तो इसका मतलब है रेस्ट एनर्जी is mc square, but when it is moving, its energy is gamma mc square. Of course, when something is moving, we have added energy to it to make it move. So the energy has increased. Yes? So, but there's another important thing here. Let's try to connect it with classical physics, with your mechanics course. So this is the kinetic energy. Actually, जो अगर आप वो ना देखें तो you don't get an idea के why we are doing it and where does mechanics stand. उसके लिए all I have to do is take this gamma and find its Taylor series. This is v square c square. इसकी Taylor series होती है 1 plus half v square c square plus ये I think 3/4 है या something v4 c4 and so on. If I put this gamma there, what is k? K is 1 plus half v square c square plus so on into mc square minus mc square. अब देखिए, if you only take the linear approximation of gamma, what you get? If you only take the linear, just दो term, and when velocity is small, you can always assume that you are good enough until this. अब फर्ज करें velocity जो है वो speed of light का 0.1 है, तो this term is 0.01 और अगली term क्या होगी? वो होगी 0.00001. ठीक है? So that's much smaller. So when v is smaller than c, 1 plus this is good enough. So अगर आप सिर्फ इतना ही लें तो ये आ जाएगा mc square plus half mv square minus mc square. This cancels and you get half mv square. So it means जो classically हम जिसको kinetic energy कहते हैं, that is first of all correct only in the limit when v is much smaller than c, so that you can ignore the higher order term. And the second, the classical mechanics is only the first order approximation of relativistic mechanics, which we are doing it here. And this special theory of relativity generalizes the classical mechanics that you have studied in Mechanics 101. And these type of approximations actually give you another tool to see if what you are doing is correct or not. Because whenever you develop a general theory, your general theory should always reduce to the special theory under the approximation in which that theory is valid. So the special theory of relativity है वो higher velocities भी valid है और smaller पे भी valid है. Classical mechanics सिर्फ smaller velocity भी valid है. तो जब आप जनरल जो स्पेशल थ्योरी ऑफ रिलेटिविटी है उसमें v much smaller than c ले तो आपके रिजल्ट्स जो हैं वो क्लासिकल रिजल्ट्स को रिड्यूस होने चाहिए. एंड दैट्स व्हाट दे आर डूइंग. जो हाफ एम स्क्वायर है नहीं, जो ये वाला है क्लासिकल वाला कहाँ से आया? ये वाला देखिए, the basic things comes from the definition of momentum. If you take mass and velocity, you will end up with the kinetic formula half mv square. If you take gamma mv, you end up with the general formula gamma mc square minus mc square. Okay? अब जो है, let me come towards this equation. This is perhaps one of the most famous equation in physics and science, जो कि आम लोग भी अक्सर जानते हैं. उसमें यह है कि बाज़ लोग इस इक्वेशन को थोड़ा सा इस तरह से करके लिखते हैं that they have m0 for rest mass and they have another symbol m for this combined thing. So when you have written mc square, that is that means that you have to find mass for a moving object which is different for rest mass. But we are not doing that. हमने gamma जो है वो explicitly लिखा हुआ. So this mass is rest mass. All masses are rest mass. There is no other mass. Okay. इसमें जो ये equation है is equal to mc square, which we call internal energy. Actually Einstein wrote it like this. M is equal to E over c square, which means that energy and mass are equivalent, which is valid, comes from there, but it also means that when you have some energy production somewhere, an equivalent mass given by this has been reduced. या अगर किसी चीज में एनर्जी ऐड हुई है तो उसकी मैस जो है वो बढ़ गई है. फर्ज करें ये रिमोट है, यहाँ पे इसकी कुछ मैस है. इफ यू वेट ऑन अ बैलेंस, इसको आप यहाँ पे ले जाएं, इसकी मैस बढ़ गई है. कैसे कि इसकी जो टोटल एनर्जी है वो बढ़ गई है क्योंकि इसकी पोटेंशियल एनर्जी बढ़ गई है. दैट पोटेंशियल एनर्जी इज स्टोर्ड और मैनिफेस्टेड एज इट्स मैस, एज इट्स इंक्रीज्ड मैस. लेकिन क्योंकि एनर्जी से जो मैस मिल रही है, इट्स कमिंग विद अ डिवीजन बाय एन एक्सट्रीमली लार्ज नंबर. c स्क्वायर इज 3 into 10 power 8 का स्क्वायर है, which is 9 into 10 power 16. So trillions and trillions and trillions of times smaller in terms of joules unit from energy to mass. So that's why the effect is invisible. But not only that, it still explains all the phenomena where energy is produced. For example, fusion reaction, जब दो हाइड्रोजन न्यूक्लियाई आपस में मिले, they fuse, the resultant mass is smaller than the individual masses. So जो mass difference है, where does it go? It goes into energy. और असल में ये भी, और let me take another example. बल्कि let me take an example of fission reaction. Let me just show you. So fission reaction होता है जिसमें एक जो बड़ा न्यूक्लियस है एक breaks into two smaller nuclei. For example, अगर आपके पास यूरेनियम 236 एटम हो और ये नेचुरली नहीं मिलता, नॉर्मली आपको मिलता है 235, लेकिन अगर आप एक slowly moving neutron जिसकी तरफ भेजे ना तो nucleus captures it and for a moment you get this unstable uranium nuclei. After a short while it breaks into two nuclei. Cesium, rubidium, cesium, plus it generates 3 neutron. और जो mass difference है अगर आप निकालें, mass of initial minus mass of rubidium, mass of cesium, and 3 masses of neutron, difference is huge. It's 2.94 into 10 power minus 28 kilogram, which translates into an energy of, इसको आप मल्टीप्लाई कर दें, ये रफली 3 ले लें. C square से मल्टीप्लाई करना, C square is 9 into 10 power 16. This is approximately in joules 2.7 10 power minus 11 joules. और जब हम सिंगल एटम्स की बात कर रहे होते हैं तो joule is an extremely big unit. It's the amount of energy that you need to actually you need 4.2 joules. You need 1 calorie, which is 4 or roughly 4 joules to raise the temperature of 1 kilogram of water by 1 degree, which is an extremely huge amount of energy with respect to an atom. So we don't work with joules, we work with electron volt. An electron volt is equal to 1.6 into 10 power minus 19 joules. So आप इसको 1.6 by 10 power minus 19 joules से multiply, divide करें, you get 165 mega electron volt. और ये सिर्फ एक है. अगर आपके पास 1 किलो फर्ज करें यूरेनियम है and you are able to break all of them, which you can very easily do if you just are able to break one. क्योंकि आपके पास 1 किलो यूरेनियम है, एक न्यूट्रॉन आपने कहीं पर रखा हुआ है, you just need to let go only one neutron. It breaks one atom. The one breakage of one atom releases 3 neutrons. So these 3 neutrons will break other 3 and so on, and it will explode. And that's what an atomic bomb is. That bigger atom, usually uranium, sometimes polonium, it's housed in something, and the fission or breakage of those nuclei releases energy. And ये जो this is not bad, this is the energy. So ये इसी का मैंने ये 2.94 पर roughly 3 लिखा, ठीक है? So बहुत सारी एनर्जी रिलीज होती है, but the important thing is that not only the fission reaction but also the fusion reaction produces energy, and fusion is the fusing of smaller nuclei. For example, if you have a deuterium and an H3 atom, they fuse to make an helium atom and they produce one neutron, and the mass difference is so that an 18 mega electron volts are produced. अब यहाँ पे देखें, जो पेरेंट न्यूक्लियस था उसका वेट ज्यादा है, और जो डॉटर न्यूक्लियाई है जितने भी उन सब का मिला के उससे कम है. यहाँ पे जो पेरेंट न्यूक्लियाई है उनका वेट भी ज्यादा है, उनका कम है, लेकिन यहाँ पे ये स्मॉलर है. So smaller nuclei, when they come together, they form an atom which has a smaller weight than the individual atom. When the bigger atom breaks, it has other atoms which have smaller weight. So like darmiyan mein, if you go on from smaller, there is for example iron. Iron is a metal. If you break it, you have to supply energy. So above iron, the nuclei are such that they tend to break to produce energy, and below iron there are atoms that tend to release energy after fusing, but at iron there's a flattening. We'll actually study much more about it when we study nuclear physics. Fusion reactions. इसलिए कि देखें, सिर्फ एक एटम जो है इट्स प्रोड्यूसिंग 165 मेगा इलेक्ट्रॉन वोल्ट, और एक सेंटीमीटर क्यूब के अंदर कितने एटम होते हैं? एक मोल के अंदर 10 पावर 23, और किलोग्राम के अंदर इट्स लाइक 10 पावर 25, 26 atoms are there. And even if 10% of them breaks, you multiply this thing with trillions and trillions and trillions and trillions and trillions and trillions. It's an extremely large amount of energy. Extremely large. Of course, compared to the conventional weapons. नहीं, fusion reaction जो है क्योंकि ये smaller है atom, usually the mass difference is small. Okay, so I have a question for you. This theory came in 1905. These reactions and these things, people slowly started to appreciate it, and the first bomb was ready like in 1940s. The fission reaction was discovered by the discoverer of neutron in about 1930, and later on the fusion reaction was discovered as well. Before that, how do people thought that what's the source of energy in sun? How does sun produce energy? Today we know that sun is mostly hydrogen, and the hydrogen at the center, at the core, it is under so much pressure that there's so much heat that the violently moving hydrogen nuclei, some of them occasionally do come close enough that they can overcome the Coulomb repulsion and they enter a zone of attractive strong force that they can fuse. So that's what produces energy. But before 1930s and 40s, what was people's opinion about the source of energy in stars and especially sun? Okay, so fire is one. Any other guess? You see, people might have thought about it, right? Yeah. Everybody knew when you are in the sun, you feel the heat, and you know the snow melts, So it means that the energy is coming from with the sunlight, so and it's far away, it's producing a huge amount of energy. So where it is coming from? What is sustaining it? Any guess? Put yourself into the shoes of those people. Initially, he didn't know. Yes? So let me tell you what people thought the source was. Most people thought the source is the gravitational energy. That okay, you have 2-point masses here. They have a certain potential energy, right? And because of their attraction, they would come closer, right? So when they come closer, their potential energy decreases. So where does that potential energy go? That goes into making them go around each other more violent. So they come slowly like this when they're coming closer. So that potential energy is being converted to kinetic energy, which is being released in the form of heat. That's a separate mechanism, black body radiation, but let's forget about that for the moment. So that was the dominant thought, even though people knew that there is something wrong, because you people have tried to do the calculation, and I will do that towards the end of this course to show you that why that was not a very good idea, because you can't come up with the numbers for that size of stars and sun. So before that, so this equation not only revolutionized the thinking about mass energy, but also solved a long-standing puzzle of source of energy in the sun and many other stars as well. So let me just do one thing, then I'll come towards your questions. There's one thing that I want to point out before moving on. Let me go and write a simple chemical reaction. And it's just one example. I'm sure you know a lot of many other chemical reactions as well. You might have studied in chemistry. You can imagine breakage of glucose, etc. But let's say you have this simple reaction that 2 hydrogen molecules and 1 oxygen molecule, they combine to form water, and in the process they release 483.6 kilojoules of energy. So where does this energy come from? Right? Okay, any other guess? Exactly. Whenever there is a net energy coming out, there is always this equation that is at play. You see here you have 2 hydrogen molecule here and an oxygen molecule here. If you are able to weigh them, their mass would be higher than the resultant water that has been produced. But in chemistry, we still have that law that masses on the left side have to be equal to the masses on the right side. There's a mass balance equation. And the reason is this. Let me convert this energy into the mass that should have been reduced. So if you do that for this reaction and you find the amount of mass that is required to produce these many kilojoules, it's roughly 5.4 into 10 power minus 12 kg. Very small. And this is for the heat that is produced by 1 mole of oxygen, 1 mole of oxygen. So 1 mole of oxygen is 32 grams. So if I convert this mass into the molar fraction, the molar fraction is roughly 10 power minus 10 between the masses on this side and that side. Right now, unfortunately, in these chemical reactions where we are performing them in bulk, we don't have any sensitive mass balance that can measure a mass difference up to this size. And for all practical purposes, we can still follow this law that masses on the left side, at least in atomic units, should be equal to masses on the right side. But we should always remember that this energy is coming from this fact that when the chemical bonds are formed, the energy stored into them are released from them, but at the back end, it's Einstein's E is equal to mc square equation that is at play. Whenever we have release of energy or absorption of energy, it's always that there's a mass difference. Now, this is molar fraction. Then I divided it with the 1 mole of oxygen. So for 1 mole, you have to be able to find the mass by this part. This is 1 in trillion. Actually, 0.1 in a trillion part. So your balance has to be this much sensitive. Source is mass difference. So the mass is coming from this thing. इसका जो mass है और इनका मिला के, this is greater than this mass. No, it's not. It's neither coming from nucleus, neither coming from. It's coming from the bonds. So ये देखें, ये हाइड्रोजन है H bond. Okay, this is O bond. It's not the electronic atomic energy level. It's the molecular energy level. Yes. It's a bit, you can say, abstract to think, but that is actually how it is. When you have, let's say, 2 atoms, and when they form a bond, they release an energy. So it means after the bonding, their net energy is, their net mass has to reduce. And if you have to give them energy to make a bond, the energy stored in the bond will manifest on a mass scale in the form of additional mass. So let me point one more thing, and that is that now we can also see why we can't travel faster than speed of light. And to do that, let me try to compute the acceleration of a particle. फर्ज करें आपके पास कोई massive object, आप उस पर force लगाते हैं, it starts to move. Classically क्या होगा? Classically, you know that if you have some mass and you apply a force, with the passage of time, you should get A is equal to F over M. So if I plot du by dt, which is this is proportional to F. And as long as there is an F, du by dt would be there. So, and if I plot u, the speed will continue to increase. But let's see what happens in relativistic case. For that, to find du by dt, let me go to this formula. F is equal to dp by dt, और dp by dt कितना आया हमने बल्कि पहले फाइंड किया होगा. Okay, so here it is. M du by dt 1 over 1 minus u square c square 3 by 2. This is that. So यहाँ से अगर मैं acceleration निकालूँ, this is acceleration. So du by dt, this is equal to F over m into 1 minus u square c square minus 3 by 2. So यहाँ से देखते हैं, जब u 0 है, हाँ sorry, thank you. So ये इधर आ जाएगा, हाँ ठीक है, thank you very much. So when u is 0, आप जो f अप्लाई करेंगे, it will result in a substantial du by dt, substantial acceleration. जब u और जब थोड़ा accelerate body होगी, इसकी velocity आ गई, जब u थोड़ा हो जाएगा, तो ये factor smaller than 1 हो जाएगा. तो जितनी भी आप force लगा रहे हैं, अब उसका थोड़ा part जो है, वो acceleration produce करेगा. When u increases further, फर्ज करें u 0.5 c होगी, तो ये नंबर तकरीबन 0.5 के रफ के करीब आ जाएगा. So जितनी भी आप फोर्स लगा रहे हैं अब उसका सिर्फ आधा पार्ट इफेक्टिवली एक्सेलरेशन प्रोड्यूस करता है. As you keep on increasing velocity, the effect of you need more and more force to may have the same acceleration. So when u is roughly 1, so u is 1c, that you are approaching speed of light, ये factor 0 को approach कर देगा. No matter what you do, you can't get any acceleration. So इसका मतलब है कि अगर मैं यहाँ पे देखूँ तो velocity क्या होगी? Velocity is increasing initially, but soon it reaches a plateau, and it cannot actually touch the speed c. It will always remain c, because when you add more, this factor gets smaller. You never reach u is equal to c. You remain smaller than c. So that's why we say that massive objects cannot be accelerated beyond the speed of light. I'll come to the questions little bit later. I have to cover one quick thing before we take questions. And that is actually a relation that we will use a lot in this course. And that is that what's the relation between energy and movement? So everybody gets that point?
Yes, sir.
That you cannot accelerate beyond speed of light.
Yes, sir. Yes.
नहीं वो तो होगा अगर नहीं बढ़ेगी कैसे नहीं इस नहीं अपोजिट में नहीं बढ़ेगी. आप ये कह रहे हैं फर्स्ट करो u greater than c हो जाए तो ये नेगेटिव नंबर है कि it becomes imaginary has no meaning because of the square root. असल में वो पार्ट जो है ना आपके सवाल का जवाब है इसमें, which we are not dealing, that how to transform the relative velocity, but we can always work out and the speed would be smaller than c. Okay, so let me get another quick relation that we'll actually use a lot in this course, which is what's the relation between energy and momentum. We saw that energy is gamma m c square and momentum was defined as gamma mu. If I do this, that I square it and then I subtract p square minus c square, what do we get? Gamma square m square c4 minus c square gamma square m square u square, and we take gamma square common, m square common, and actually c square common, we get c square minus u square. So this gamma square is nothing but 1 minus u square over c square into c square minus u square. So यहाँ भी c square से multiply कर दें, यहाँ भी c square से कर दें, तो ये बन जाएगा c square minus u square. तो c square minus u square इससे cancel हो जाएगा और यहाँ जो c square से multiply किया था उससे आ गया m square c4. So we have this relation that we will use a lot. Let me write here e square minus p square c square is equal to m square. Light जो है we'll see later if we treat it as particles, photons, then its mass is 0. So which means that for 0 mass, E is equal to Pc. So why do you say M should be infinite? So this is valid for massive object. So first of all, this is not valid for the light. Okay, so this is valid for massive objects. Light, there's a way of saying it, okay? It doesn't have the mass in the usual sense, it has momentum. It's better to say it has momentum. We'll see that why it bends even without mass. So space-time theory. फिर भी क्या होता है? Yes, so you see, that's why this equation comes handy. Even when m is 0, it doesn't mean things can't have momentum. P is equal to E over C. The photons have energy. Even for massless photons, there's a momentum P is equal to E over C. So momentum is an intrinsic thing. It's something you can say different than the mass. So in classical physics, the light is electromagnetic waves. They are not particles. Okay, so let me summarize and tell you one more thing, which might answer some of your questions if you have. That where do we come from? In a sense, that where do the elements and things that we are made up of, they come from? Okay? So we saw that in fusion, in stars, the hydrogen nuclei are fusing to form helium. And that is happening in sun. And actually sun has already consumed about 7-8% of its total hydrogen reserve, which still means that it has like 90% still left. So there's plenty to go, about another like 4 billion years it can survive with this food. But in stars, what happens that once they run out of hydrogen, they start collapsing again. And actually, the initial part, when a star is formed from a big cloud of gas and dust particles, it's cold. When it's coming together, the gravitational pressure energy is converting to kinetic energy and heating it up. It's coming together, the internal energy is increasing, it's condensing, and once it reaches a point where it's hot enough inside to ignite fusion, the fusion starts, and because of the immense radiations coming from the inside, the collapse stops, and the star has a stable life. And it continues for billions of years until it runs out of hydrogen. It starts collapsing again, at least its inner part. And it's collapsing until another higher temperature is reached where heliums can fuse together to form carbon, oxygen, and other heavier atoms. So you continue until you run out of helium and you have mostly carbon and few other elements. That's why we have abundance of carbons finally. And then you condense until the carbon fuel cycle stops. And you continue until you reach iron. Or iron ke baad dusre atoms and they are formed because iron nuclei can capture some particles here and there, and we can get some trace elements, let's say silver, gold, etc. That's why we have very few of them anyway. And that is if the mass of the star is too high. If it is small, it can very easily switch off all the mechanism and becomes a dead black dwarf. It's called black dwarf because it's not radiating anymore. And if the star is too big, it can actually collapse under its own weight after iron has reached. Then the outer part explodes in a supernova, and in the explosion, some of those heavy atoms, they are also scattered, and that another giant dust cloud is formed, and the solar system is actually made partly from this second dust cloud. And that's where we have other elements other than hydrogen, helium, and 4 rocky planets in the inner solar cell, etc. Okay, to summarize, we have covered the relation between energy and momentum, and saw the application of, I have a small clip today to actually say again the same thing that I have told you. Maybe you hear it from somebody else and believe them more than from me.
fast light flow and zero light flow.
Give the options. Oh, what's the question? So this is a small clip
Deep.
about the sun.
Center. The core. The sun gives birth to light. Forged in one of the most violent reactions in the universe. If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse, and that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
So there's a question for me. Where do you think the energy goes that is released when any of this nuclear reaction happens?
While billions of stars are scattered.
Okay? I have another one to show. So when a nuclear reaction happens, and let's say two atoms fuse together or one breaks into a few, and we say that this much energy is released. In what form does this energy is released? In most of the cases, actually this is released in the form of kinetic energy, that the reaction product, it travels with an extremely fast speed. That's the initial form in which this energy is released. It's released in the form of kinetic energy. For example, the kinetic energy of the of the product. For example, here the helium and neutron which are produced, they travel violently, and then they collide and may produce photons and other forms of energy. Through electromagnetic waves, mostly in light and infrared rays, but also in form of particles. Light ki usually we don't say kinetic energy because it's not massive.
But way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself. And towards the centre of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our Sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the Sun, this will be the beginning of the end.
What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on it anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang, the outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star billions of years ago before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually I think ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
Okay, so that's it for today. Thank you.